Hello, everyone. Welcome. We'll be starting in just a little bit here. Give maybe another minute or so for people to come in. All right, let's kick this off. Again, hello, everyone, and welcome to the Efficient Random and Base Vibration Analysis for Printed Circuit Boards webinar. My name is John Shu. I'm the Simulation Services Director for MyHTT, and I'll be your host today. So first off, though, I want to just cover real quick, why should you pay attention today? Main reasons are, I believe that you can get more accurate results significantly faster with our tool. But before I get into that, let me give just a broad overview of MyHTT. If you haven't heard of us, we're a software-driven engineering solutions company. We're a Siemens Digital Industries #1 global partner. Actually started in space about 40 years ago, primarily on the thermal side, building thermal analysis software. And we have a staff that's above over 200, that's 75% scientists and engineers. And we also author over 30 software modules for the Siemens portfolio, in addition to our own software as well. Now, what do we do in general? We have three main components to our company. We're an engineering software development company. We do consulting and integration, and we're a digital solution distributor. So basically we sell software, we develop software, and we also support and do projects and services as well. In the areas that we work in, if you look at the wheel on the right side, you know, from PLM to design, simulation, manufacturing, we have a large and growing AI and IoT team, software development, and automation. We cover the full breadth of the software-driven engineering solutions. Now, I want to ask a question just to kick things off and see, what is your experience with sine and random vibration? So I'll go ahead and launch the poll here. You should see that pop up on your screen, and you can start clicking on there to vote. I'll give people a little bit of time to respond in there. I always like to get a feel for the audience, how experienced you are or not. Often we get people who've been doing this for years. We get people who haven't done it before, just interested in checking it out, and everywhere in between. Usually a pretty good mix, which looks like kind of what we're getting now too. See, I'll close the response here in just a second. Looks like everyone's done voting. I'll close that and share it. So yeah, pretty good mix per usual. So we have about a third of you use it very frequently, a little more than that, done a little bit, and then about a quarter of you familiar with the concepts but haven't really done it. So that's great. That's a good mix. I'll try and cover topics in a way that's useful for everybody in this meeting. So let's carry on. The agenda for today, well, I'll talk about why do we care about vibration to begin with. I'll do kind of a really quick intro on some of the ECAD, MCAD tools in the Siemens portfolio, and then talk a little bit more in detail about our structural analysis toolkit. Then I'll dig in more to the processors that are in those, sine random processors and the others, and I'll hit a little bit on random vibration theory, try to make that in a easily accessible way. I'll do a quick demo with our toolkit, And then we will talk about PCB fatigue life. You get the results, what can you do with those afterwards? So to start, why do we care about vibration? Well, let's think about where vibrations come from to begin with. In a lot of the products and industries we're looking at, if you're in the automotive or anything that travels along a road, you get vibrations from moving along an uneven surface, going through the suspension into the vehicle, shakes everything. If you have a plane, you get the aerodynamic vibrations and loads, takeoff, landing, the engines, anything moving causing a vibration. And if you have think of satellites or rockets, often during the launch, you have vibration from the engines. You have a lot of acoustic noise that's shaking everything, and then aerodynamic loads that happen during the launch as well. Now, for our purposes today, I bring up these three because they're some of the main industries you tend to look at random vibe and bass-driven vibrations in, and these all have electronics in them, and they're going to continue to have more and more electronics. We just keep adding more into it. But when you look at the vibrations, what you get from that is a time history of amplitude, acceleration amplitude over time, and that's your input, that's your vibration, that's the actual environment that you're seeing. Well, if we look at take a step back, look at the engineering development process, kind of your typical sort of V curve design, build, and test. Where do the vibrations come in here? So we start with requirements. Generally, if you have something like a satellite sitting on a rocket, you're trying to design the satellite, you have input vibration levels, PSD curves, acceleration curves that you get from standards. These are known curves. They've enveloped the response from the rocket, from the launch, and you are designing your part to these requirements. And then when you're doing the design and analysis, you take those same requirement curves and you're using those to analyze your model. So you would take either, you might take a full satellite model, or you might take like individual components of that satellite and analyze them to the specific PSD inputs, acceleration inputs. And then you go and build it, and then you build the components, build your satellite, and then you're testing on the back end often, and you're often testing with a bass shake on a shaker table, so it's bass driven vibration, and that kind of matches the analysis you're getting, and you're checking to make sure this part that you designed and analyzed, does it actually pass? Are you seeing exceedances like accelerations responses poking through that profile, to make sure that your part, and you can also test for lengths of time to make sure that your part will survive the environment that you expect it to see. So if we take a bit broader step back, what are the benefits of a more efficient design process? You've probably seen, there's variations of curves like this out there, but it's the idea that during the product development life cycle, over time, as you go deeper into it, the longer time on the cycle, you have more costs committed to the project. The cost of change starts to increase, especially as you get closer to the end, and the ease of change, how easy it is to change, it gets a lot harder to change, basically. So what you're looking to do is find ways to shift things to the left on that curve. So what I like to think of, if you have a solution like, for instance, our structural analysis toolkit that's more efficient, that's faster, that helps you move left. It helps you, you've probably heard the term fail fast. If you're doing a lot of design iterations, it helps you go through those quickly to find the problems and solve those without taking weeks and months to set up an analysis and run it and then have to back and redo that iteration to take the same amount of time. It just moves you to the left, makes everything easier and cheaper. So quick intro to Maya's structural analysis toolkit and some of the Siemens ECAD and MCAD tools. I won't hit on this in too much detail, but I just want to point out for anyone interested, Siemens has a full suite of capabilities for connecting your electronic CAD to your mechanical CAD all through the design process, from collaboration upfront during the design, having that rigid flex design collaboration, being able to do review and validation, accepting previewing and accepting changes, and then putting it down into the manufacturing phase where you can still look at the CAD and everybody's basically on the same page. There's a continuous digital thread through all of that, and you're working in the same tools together. It just makes a much more efficient process. And if anybody's interested in anything like this, definitely reach out to us. We can help you explore what works best for your process and your workflow. Now, in addition, one of the products that Maya actually develops is PCB Exchange Connect. It allows designers and analysts to collaborate on a web-based platform. So this is fully on the web, and you can visualize, query, compare, measure PCB boards and panels. You can do searches for different components. It's a really great tool for making sure everybody's on the same page and can access the same information. In addition, we also author the PCB Exchange product that is within the Siemens portfolio that allows you to take the ECAD and move that information directly into your simulation models as well. And I'll show that just very briefly. Now, the structural analysis toolkit, what I'll primarily be talking about today, this is for SimCenter and MSC Nastran. Directly manipulates the OP2, that's the results files. So it gives you results. You can look at the results in SimCenter FEMAP or SimCenter 3D. Can run in batch, creates automated reports. And it's a fast and accurate random and sign base-driven solution for Nastran normal modes. So it uses the solution 103 from Nastran, your normal modes run, and then does the random and sign vibration analysis on top of that. Now, it accounts for non-Gaussian probability distributions. So that means you can be a lot more accurate than just trying to fit everything to the zero mean Gaussian distribution. Computes peak composite failure metrics. So if you have laminates, you have composites, you can compute the failure metrics in your random analysis for those. It accounts for model truncation with ResVec. It can generate stress margins of safety, processes very large files, so greater than 1 terabyte, no problem processing those. And this is a tool that's been in continuous development at Maya on R&D since 1998. We continue to release iterations and have another one about to release as well. One of the biggest things with the biggest selling point and reason why a lot of people use this is because it's fast. So I have an example here. This is not a PCB, but it's a satellite. You could have PCBs in here. This has about 162,000 nodes, 131,000 elements. Kind of a mix of different types. Has laminates in there as well. If we're looking at 34 modes, OP2, so that's the results file of 1.5 gigabytes. So on Nastran, your standard Nastran solution 111, your standard random vibe, other software competitors might take over 30 minutes to run the random analysis on this. With SA Toolkit, that's solved in 8 seconds. A massive improvement in time, over 200 times faster than Nastran products and other major FEA solvers. And that's a big reason why a lot of people use this. Now, I'm going to talk a lot about random and sign vibration, especially random. That's the main selling point. We do have other processors in there, so modal, energy, stress, grid point forces, element forces, mass summaries, just some other tools to give you different views of the data, make it efficient for you that you can put into your workflow as you see fit. But it's time for another question now. Let me ask you, what are your biggest pain points when setting up and running and post-processing random and sign vibe analysis? I'll launch that poll again and go ahead and have you vote in there. I have my own personal opinions on this, but I always like to see what other people think on where they see the pain. What's the biggest problem? What if I could offer you a solution to something, what would be most beneficial to you? See results coming in here. Actually, a really good mix. A little bit of everything here. Still a few voting. I'll close it here in just a second. Let everybody read through those responses. Those ones are a little long, and I gave you a lot of options here. All right, we'll go ahead and close that, and I'll share the results. So, all right, actually a good mix across the board. The biggest one, confusing or complicated to set up. Honestly, I'll agree with that. If you're just going, especially if you're just going straight through Nastran, yeah, I've had to do it through the text file before, and man, that's a pain. Developing an accurate but coarse enough model, yeah, that kind of goes to solve time as well. Can't easily get all the results you want. Yeah, that's another problem I've seen a lot. A little bit across the board from everything. All right, we'll hide that. And let's go on to the next section. Let's talk a little bit more about the structural analysis toolkit. So the processors in it. And again, like I said, I want to hit a little bit on random theory for you. So let me talk about the modal processor first. This is something that honestly you can get post-processing of modes, and you can look up a lot of this data. A lot of companies have Excel spreadsheets to process this. This is just one benefit of the toolkit. It easily spits out some of these. I like to have the the modal participation, cumulative percent modal participation factors in there. You can kind of see which modes and in which directions. That's useful for design to figure out where you might expect to see problems. And then if we look at the energy processor, again, one thing I like about this is you can use groups. So these are groups of elements. For instance, in that satellite model that I had. So you can see on the modes, it's just a nice quick visual of like, okay, which parts of the model are responding to which modes, and see where that energy is coming from. Now the sign processor, I'll mainly just talk about this one, but it's efficient and accurate base-driven harmonic vibration simulation. It determines phase-consistent von Mises stresses. It's parallelized and can be run in batch mode, so that helps it solve quicker if you've got big runs and a lot of runs you're trying to do. And it's accurate results using Nastran eigenvectors. Again, it's using the Solution 103 modal analysis from Nastran. It can compute von Mises stresses and associated failure metrics. It does the composite ply stresses and failure metrics, handles modal truncation with residual vectors, and it gives the same exact results to Nastran Solution 111, or at least for the results that Solution 111 is capable of spitting out. We are able to do a few results it can't handle. For the random processors, it's much the same. Again, many of the same points. It's efficient and accurate base-driven random vibration simulation. Now, we use some state-of-the-art integration schemes. It's done a subset of results. No need to specify integration frequencies. The peak results, they correspond to a user-defined confidence level. I'll explain that a little bit more. That goes into the idea of 3 sigma results. I'll talk about that more later. Again, this is parallelized, can be run in batch. And once again, accurate results using the Solution 103 modal analysis from Nastran. Does the von Mises stress, associated failure metrics, again, does composite ply stresses and failure metrics, so you can run your laminates, your composites in this, and handles the modal truncation with residual vectors. And if we look here at types of vibration, so talking about the theory a little bit, well, if we're looking at sine vibration, random vibration, so I kind of like this chart I found online to show different types of excitation, kind of categorize them. I always like categorizing things in a visual way if I can. Sine vibration, it's deterministic. So the amplitude is known at any given time. It's repeating, it's a repeating oscillation, and it's harmonic. So a single sinusoidal function, single frequency, single amplitude, your standard sine wave there. Now the random vibration, the amplitude at any one time is not known, so it's random. It is stationary though, so the mean and standard deviation are independent of time. It's ergodic, so the probability information from, like, you have one sample is of a decent enough time is representative of the entire sample of time. And the form of its probability distribution is Gaussian. So the RMS and peak values, they'll correspond to a user-defined confidence level. That idea, if you've worked in industry and used this, you might have heard like 1 sigma, 3 sigma, peak, RMS. That's what we're talking about there. So this is the idea that in general, the time history is random. You don't know the amplitude at any time, but any like representative time of representative acceleration time history of that data, of that event, is going to be representative of all the others. So you can use those, and you can define this and analyze to it. If it wasn't that, it would be more of a transient response, and you'd have to do some transient analysis. Now, random theory, what we're doing, so we've got these time histories, and when you're looking at those, you've got your acceleration over time, and it's a bunch of frequency content in here all at once. And what you're doing is, if you have a Gaussian probability distribution, and the equation might look like this, when we're talking about RMS and peak values, what we're really saying is, so RMS is your 1 sigma, and we're saying that over that time history, the acceleration data, 1 sigma, 68.3% of that is within this 1 sigma range. And then you go 2 sigma and then 3 sigma, 99.7% of all this time history falls within the 3 sigma range. And this is just the idea of taking a probability and determining, okay, what am I enveloping enough? Am I designing to the right level? Obviously, you might not be able to design to 1 sigma because, well, that means, like almost 30% of the time you might have loads, accelerations that exceed that. Well, you got to design for those. On the other hand, 3 sigma, we can live with not designing for that 0.3% probability. And then you add safety factors on that to cover, but you can't always necessarily design for 100% of loads, but we choose 3 sigma level. So we're 99.7% confident that we've designed for that much of the loading. Now, that was looking at a Gaussian distribution, zero mean Gaussian distribution, but not all of the random analysis is Gaussian. So results you want to look at, like von Mises stresses, composite failure metrics, and nodal vector magnitudes, those might not be a zero mean Gaussian distribution. So why does that matter? Well, traditionally, your standard tools that you would use for random vibration analysis, the user actually needs to scale the RMS results to peak using a ratio. So So basically often you'll get the RMS results and you just multiply by 3. That's what most of the standard tools do. That's not always going to be accurate. In fact, in this, we have a reference of an instance we calculated where there was an error of 20% here. Just taking the RMS multiplying by 3 gave a 20% error, actually, so which meant in this case it was over designing the part to what the real peak was. We've also seen instances in the other direction too, so it's not like you're always conservative. We've seen some instances with composites, especially where this 3 RMS would have been lower than the actual peak based on the actual distribution, which means you're under designing your part and you're more likely to have it fail. So the structural analysis toolkit, one of the big benefits of this, so it's using these advanced stress algorithm. It determines the actual distribution of the derived results. So again, that, the von Mises, the composite failure indices and such. And so it computes the statistical measures. You don't ever have to multiply your RMS by 3. It's calculating the correct peak for you. And it's the only commercial random solver to compute the laminate composite first ply, failure indices, strength ratios, and margins of safety. So again, just going to the accuracy in addition to being fast as well. And speaking of fast, let's look again at the performance here. So the model, I believe I shared that spacecraft, simple satellite example model we put together that I've shared before. If we compare it directly to Nastran Solution 111, and you look at, all right, output requests to get accelerations, we're looking at it takes 8 seconds for structural analysis toolkit versus 24,000 seconds for Solution 111. It's 3,000 times faster on there. For stresses, to be able to pull those, again, we're talking seconds compared to minutes, hours. And then when you're looking at trying to pull other information like, failure indices, margins of safety, laminate strength ratios, you can't even do that with the standard Nastran Solution 111. And still, although it's not, we're not under 10 seconds anymore, but we're still only looking at like 3 minutes of time to pull all that information together, to grab all that in one random analysis run with Structural Analysis Toolkit. Now, one last thing here I want to hit on is, and this goes to the accuracy as well. So often you need to select the random excitation frequencies at which you run your random vibration. Now, the issue here is you don't want to select too many because you're going to run slower, but you don't want to select too few because your results won't be accurate. But in addition to that, if we have an example here where, all right, the red PSD I show, we've selected 198 excitation frequencies. We want to, these are the points that the random vibe is going to analyze at. So we had selected more, and then the blue one, 125. Well, you'd expect the red one to be more accurate, but there's actually a 16% difference in the blue one just because it has its frequencies more in the right locations, lining up with the frequencies in the model. It's more accurate. Now, the nice thing about Structural Analysis Toolkit, it doesn't require you to choose these excitation frequencies. So the FREC 3, FREC 1 cards that you might fill out if you're familiar with Nastran, you don't have to set those. It chooses them already, and it accurately runs them and makes sure you get accurate results every time, so you don't even have to worry about it. Now, I'm mentioning a lot about Nastran, obviously, because that's the results that our Structural Analysis Toolkit uses, but I'd like to get a feel for what software do you use for random and sign vibration analysis. And I'll launch the poll here and let you all vote. We have some options here, very Nastran and Siemens centric, but also interested if you use other tools as well. Again, we're getting a pretty good mix across the board here as the votes come in. It's a really good mix in the audience in general today on all the questions. A lot of different experience across the board. All right. This one's all right, almost done here, and I'll go ahead and close the poll. Okay, and share the results. So about a third of you are using other solutions. I have as well. I've used ANSYS, for instance, and Abacus. And then a good number of you, actually about a quarter of you, already using the Structural Analysis Toolkit. That's great. You're taking advantage of all this already. SimCenter 3D Response Dynamics, another quarter of you. Yeah, actually the Structural Analysis Toolkit, our solvers are what drives the SimCenter 3D Response Dynamics. So you're taking advantage of Structural Analysis Toolkit speed and efficiency already. There's a few things that our toolkit does that they aren't in the response dynamics, but the main solver's in there. And then some of you with, yeah, just standard Nastran results as well. So I'll go ahead and hide that here and go on to the next part. So now I want to do a demo for you here. And let me go ahead and open up my model. So today we wanted to talk about PCBs. I know I was showing a spacecraft, and there's often electronics boards in there. This obviously isn't a spacecraft PCB. This is a very, just simple dummy graphics card model that we put together. One thing I'd actually like to point out here is that if we look at the board here, and talking about I mentioned PCB Exchange. So we got a model that had this PCB geometry in here, and that PCB Exchange tool we talked about, the really cool thing it does is if you have all the information for the electronic components in here, and we were able to very quickly convert that to a structural model. So our PCB Exchange automatically created these RBEs and created lumped masses for all of those PCB, all those components on the board, and put them all in the right place. That's awesome, because I've done PCBs before where you're trying to like split shell elements, you're trying to put RBEs, grab the right area, calculate, you're doing it all by hand. So you don't have to do this by hand anymore. You can do that directly in here. Now, looking a little bit more, so I've already run the modes. Like I mentioned, all this is based off of the modes. So I have the modal results in here. And you can see the board is kind of a standard board inside here is connected. You bolt it in on the end, you plug it in there, constrain it. One thing to note, and this will get into the fatigue a little bit later. So because this board is kind of cantilevered and deflecting, I've just created this RB3 here to track basically the overall deflection of the board, which we can then use with an MPC to compare, to get the relative deflection between, the kind of the rigid body cantilevered displacement of the board in relation to the deflection of the actual board, the bending of the board. That's going to come in, that's going to be a critical component to the fatigue calculations I'll talk about later. Now, let's go into the Structural Analysis Toolkit and take a quick look. And let's see how we set this up. So this is the Maya Structural Analysis Toolkit interface. So I'll come in, and again, I'm pulling the OP2, the results file, from the modal run, and I'll quickly read that in. If you have a much larger file, you can do like a quick open where it's not going to take time to read through your, if you have like a terabyte model, you might want to take a little bit more. But that was about half a gigabyte file that I read in. I can import Nastran file. I can import groups as well from the Nastran file. So I've created some groups in here just to be able to easily choose where I want results. You're just reading the Nastran dat file. Click OK. Now the toolkit itself will look at, based on when it reads it in, it'll determine, based on the results you requested, which processors you can use. So you can see here, I didn't request some of the grid point forces and such that would be needed to do, the grid point force processor, energy analysis and such. But we're going to be looking at the random processor as well, which opened up on my other window. Now, to set this up, it's pretty easy. It just walks you through the workflow to set things up. So I'm going to start with a base acceleration PSD. Now I have one already created here that I'll just pull in. This is just a NavMat PSD, I believe, that I already created from a file. You can also enter them in, point by point here as well. Now I'm going to apply that. I've done that in the X direction. We'll hit apply. And then I want to run more than one load case. So I will run one for the Y direction, and I can initialize it from that one I already had in and apply. I want to do the same thing here. I want to run one in the Z direction as well, which if you look, actually that's the main direction of interest for this PCB will be in Z. That's what the direction the PCB is going to be deflecting in. I don't know why everything's opening on my other window all of a sudden. I'll click OK. And so now I've got my PCBs. I've set up 3 load cases in X, Y, and Z direction, and I just use the same PSD for all of them. You might have different PSDs. Now frequencies. Again, I'm going to use all the modes. I'm going to include the ResVac static contributions, and I'm just looking at the full band of frequencies here. I'm not limiting that in any way. For modal damping, you can choose the damping. Again, I'm just going to do a simple across the whole frequency domain that I'm looking at. I'm going to do kind of a standard 2% damping there. You can input based on your Q value. You can look at the plots. My plot's pretty boring in this case. And then analysis parameters. So again, this is talking about the fact, your peak response. So we want to get what is the 3 sigma. But what is happening here is I'm just telling this I want a number of standard deviations. So I want 3 sigma response for my peak, but this isn't just multiplying by 3. This is calculating the actual distribution for all the results and giving me the 3 standard deviation response, the actual 3 sigma peak response, not just multiplying by 3. You can do it by confidence level too. So again, 3 sigmas equal to 99.73%. And then these standard options here are usually the best for this. Now we've set up how we want to run it. Now we're going to set up some results here. So I'll create some results for a stress case, and I want to select some groups. So you can see that I've brought in I read in some groups here. Let's say I want to look at stresses on the bottom enclosure and the top enclosure. So that's sitting around the PCB. I'll look at those together. Click OK. We need to put some results in here. I'll actually keep that kind of low. You do need to know what units your model is in. So in my case, my stresses would be in megapascals. So if I was doing aluminum or something, I might do 240,000 megapascals. I'm actually going to keep it a little bit lower just to see something a little more interesting. Click OK. I've got my stress case. Now my outputs. All right, so I had a stress case, so margin of safety. If I had multiples, I could select multiples. I only did one. I want to read the binary. That just is an input that I can read into SimCenter 3D. All right, so I got my peak margins. I got my margins of safety there. Let's look at accelerations. So for the accelerations, let's get the 0 crossings, and I just want it on everything. all the nodes. Now, I also want to look at acceleration PSDs for just the displacement nodes of interest. So that'd be, I created a group for what I called my displacement nodes. This is going to be the base driven node, and then the nodes for that give me like the relative displacement of the board. So let's see, do that. Now displacements, that's one of the primary things I want to see. And again, I could do the PSDs with that same group for the displacement nodes. Okay. And I also want to be able to plot displacements in here as well, if I wanted to. So I'll bring those in. Let's see. Okay. Let's see. And then actually, I think I forgot. I want to see acceleration binaries too, because I want to be able to read in these displacement PSDs. Again, one of the nice things here is I can just keep coming in and adding a whole bunch of results because it's pretty fast, and I can look at all this together. You can look at stresses. So let's look at stresses on that outer, those outer components. Let me find my shell groups there. Yeah, I want that one, and I want this one. I want the binary there. Peak stresses, results. Yep, that all looks good. All right, so that's pretty good. I've got a pretty good mix of results there. You can ask for composite failure metrics as well if you have like the failure theory set up in your model and the correct stress limits as well. So we'll click OK. We'll click OK on that, and then we'll go ahead and hit start. And it'll run here. This one I created quite a few results, but this one's going to be pretty quick. Just a couple more seconds, I think. Come in here. I did request a lot of stresses though. So, oh, there we go. We're done. So it took about 18 seconds. I requested a lot of results. It's also a small model, but you saw before, 100,000, 160,000 degree of freedom model solve in seconds as well. Now, how do we look at these? It's pretty simple. So we can just come into here and go back into, again, I'm working in SimCenter 3D here. I'll just create a new solution that I'm going to read those results into, import them into. And we'll come down here and I will load those results. And I'm looking for this. You can see that the SATK creates its own OP2 file with the results. So I'm reading that one in. And then there's some companion result data I want to add as well to that. So that's in a different file, the .bun, the bun file, we call it. Read that one in. And then let's go take a quick look here. We'll see how these results come in. So if you remember, I had 3 load cases, X, Y, and Z. You can look at the, root mean square von Mises elemental stresses. You can see here, okay, yeah, right where we've got some bolted connections, we're seeing higher stress. That's something you would expect. And if you remember, I requested stress results for the outer enclosure. And then if we look here, we can see, you can see displacements, you can see peak acceleration for the entire thing. We could look at just the board if we wanted to and see, okay, how's the board looking in there? Again, you can see these are your rigid, your lumped masses that represent the components on the board. They're connected to it. So you can go through here and just look at all your stress results. Basically, there's your failure indices for that I requested as well. Now, one thing as well, you can plot in here. You can plot all those PSDs. I also like to look at I chose to spit out some HTMLs, and I can come in here and look for the load cases. If you look at like your acceleration. So I like this because it spits out these HTMLs. I don't even have to go into, it's a really easy way to do a quick check. I don't even have to go read in the results. Um, I chose my base excitation node, and it's a quick check to see, okay, my PSD looks like what it should be. And then from there, you can go and say, okay, well, I want to see displacements. You know, what do my displacements look like on the different nodes in here? And you can look at the frequencies. Just a simple quick check. You can also plot them in here as well. And that's basically it. It's pretty fast, pretty easy. You saw that I was able to set that up quickly. I kind of took a while to talk through it, but if you're clicking through, you know, a minute to do your setup, just seconds to run your analysis, and then you're quickly just jumping in and looking at results. So let's say, you know, we're looking at a PCB. Now, what do we do with these results? What do we do if we want to look at fatigue life here? Well, let's talk about what causes fatigue generally for now due to mechanical vibrations. So we're not going to talk about thermal in this instance, although we do, we have a lot of experience with thermal fatigue of PCBs as well. So if you remember, let's assume we've got a PCB, you've got some component on it. Here we'll assume just, you know, wire, solder connection, and you take that time history and you apply that to it. And what you're going to get is a deflection of the PCB here. And then the big thing is you're going to get relative motion between the component and the board. And that's causing these wires to flex and strain and eventually break if they get enough cycles of high enough energy. So one of the most common standard and industry methods for calculating this that kind of makes it pretty easy is the Steinberg method. This actually comes from a book I referenced at the bottom by Dave Steinberg. I highly recommend if you're doing anything with, you know, PCBs and just random and sign vibration in general, that book is a great reference. Often in industry, we just look at this one equation, but just in reviewing that book prior to this webinar, I remembered, oh yeah, there's a lot of great information in there. I highly recommend it. You pick up a copy. But what you're doing in general, the way you set this up, it's kind of based on a lot of empirical data. He's able to determine that put together this equation that says for a deflection at the center of a board, of a PCB board, he's able to determine what is the 3 sigma PCB displacement, so your displacement to the 3 sigma level, that gives you about 20 million cycles. Kind of an assumption that if you can have your components good for 20 million cycles, you're in good shape. So this is all based sort of on geometry. It's based on like a sinusoidal shape of the board. It's actually, are some caveats. This is based on being like a rectangular board being held, simply supported on all 4 sides. And so you just have to put in components. You know the length of your board, you know the thickness of the board, you know the length of your component, you know, and you use the edge parallel to the component. So with a square component, you might want to check both edges if it's a rectangle, not a square. There's different constants for different types of components. So is it a ball grid array? Is it using, you know, it's kind of your standard wire solder connections? There's a whole list of those. And then there's an R value for relative position factor for the components. Now it's rather limited in that sense, but one thing that I've seen and that we've actually done at Maya as well is to look at taking that R value out of it and just pulling sort of the shape of the board or your angle relative to the component, taking in that information directly, that instead of having to just be limited to like, you know, is it at the center of the board? Is it, you know, halfway between the center of the edge or halfway between the center and the corner? So there's some stuff you can do to try and go beyond this, but you do need to be aware of the limitations of this equation specifically, so that you do your calculations correctly. Now, you've got your displacement. So this again is telling you, okay, if as long as my 3 sigma displacement is that value or less, I should be good for more than 20 million cycles. So how do you do some of that math? Again, you can use an equation that's basically calculating along the slope of a, I'll say an SN curve. That's what we're used to for fatigue, but in this case, the stress is proportional to strain, proportional to displacement for a linear system. So you can again calculate that. You can calculate you've calculated your limit from Steinberg based on that equation. And then with the relative displacement that I showed that you can get out of your model directly, you can see, okay, how many cycles to failure is it for that displacement? And again, in the book, there's some information about this B exponent value, which, for PCB component lead wires, 6.4 is used. And then you can use your miner's cumulative damage index and to calculate up your failure. Now you can do some interesting things with this as well. So you can take your, look at your either the main frequency and base your number of cycles per second off your main frequency, say it's 250 hertz or something. You can also use, if you noticed, I requested positive 0 crossings. So the number of times that my displacement crosses 0 on the results. So you can use that because you'll get a positive 0 crossings in sort of a frequency component too. So the number of times per second. You can use all those to calculate your cycles. You can even look at it you can go a very conservative standpoint of saying, okay, I'm just assuming that anytime I cross, or for that frequency, anything, I'm just assuming it is the peak. It's the highest level. So you're just assuming, well, everything's this value. It's the 3 sigma. But that's not the whole thing. So you can do something where you do a 3-band distribution, and look at, okay, how many cycles reach 1 sigma, how many cycles 2 sigma, how many cycles 3 sigma, and add those up to get cumulative damage. So unfortunately, I don't have enough time to dig in deeper to that. But let us know if you're interested in digging in a little more on that. We might even put together a webinar on that at some point as well and try and explain through some of this as well. But I just wanted to give you today some point of reference, a specific reference that you can go to that book. There's other references out there that help. I find vibrationdata.com is really good. There's a lot of free resources, and then frankly, really inexpensive access to some calculators as well. It's always good sometimes to just see it listed, see something explained in a different way. But to go back and revisit the structural analysis toolkit and to kind of close this for today, our structural analysis toolkit, it's a best-in-class tool for simulation of base-driven random and sine vibration. It's got unprecedented performance. It's just fast. When it's so fast, that means you can do larger models. You could even do a satellite model where your PCBs are actually in the model instead of doing things separately like you might normally do, because it doesn't matter if you add an extra 5,000, 10,000 elements and nodes into that model. It's going to solve quickly in seconds. It's also accurate. So again, some of the key things, it can do the composites, the laminate failure metrics. It handles the phase consistent von Mises stresses. It picks the right frequencies for you. And in addition, it also actually does the accurate 3 sigma results for you as well, not just multiplying by 3. So with that, I want to ask just my final question for the day. And I want to ask how would you prefer to learn more about Structural Analysis Toolkit? Or I might even add to that just any of the ECAD or PCB tools that I talked about, or some of the fatigue as well. We offer information in a lot of different ways. It's always good to see what people are most interested in. So this one I'm seeing a lot of people like the self-guided. I tend to as well. But, oh, now we got a few more responses. And I will say, anybody who's interested in a one-on-one meeting, yeah, definitely feel free to reach out to us, or I think we can reach out to you as well and touch base and see how we could help you, or see what your workflow is and see if there's something we have that could help. So yeah, I think everybody's pretty much done voting. I'll share that real quick, although that one's not as interesting to share, but a lot of people like the self-guided help documentation or tutorials. So I will open up now for any questions. Thank you again for everything. If you scan the QR codes, one's for information about myself. Frankly, probably not as interesting as scanning the other QR code that'll get you information about the Structural Analysis Toolkit and allow you access to a white paper there. So if you have any questions, now's the time to ask them. I'm going to open up the question box here I'm looking at and seeing a lot of, yeah, there's quite a few questions already. I'll just start walking through, answer some of these. Is the webinar going to be registered? I assume you mean, is it going to be available? Yes, it's recorded, and we will put it will be sent via email in 1 to 2 days, and we tend to post these on our YouTube channel as well, so you'll likely see that up there later. Let's see. Are the binary formats just for NX simulation, or will they work for FEMAP too? We do have the results, so those will read into FEMAP, I believe. Actually, I'll be honest, it's been a little bit since I used it with FEMAP, but you either use the binary or you use one of the other options there. You check those, and you can read all those same results that I was showing in SimCenter into FEMAP as well. Let's see. Any other questions we have here? Can you explain a little more detail of why SATK is faster than Nastran? So we cover some of that in our white paper. In a nutshell, it's the high performance integration schemes, von Mises stress and strain estimation, parallelization, efficient OP2 file reader. There's a few things in there. Does SATK do transients too? No, at this time we don't do transients. It's the sine and random and the other processors I showed. We're always thinking about what's next for the product development and what else to add though. So it's always good to hear from people what they're interested in. I'm sorry, I might not be able to get all the questions here right before we end. Transients are key. Take forever in NX. Yeah, transients take forever in everything, I think. I'll agree with you there. That's why I like when I can use random instead. How do you verify your simulation? That's actually a good question. So again, to answer that, probably the best answer is basically that our results match solution 111 in Nastran exactly for the same results that it gives. So we give the same exact results, we just give them a lot faster. And there's been a lot of validation and verification of Nastran results over the years. So I would say we validate by matching Nastran results. I think, unfortunately, I won't be necessarily, I'm not sure I got every question in there. I think I got most of them. There's quite a few there I'm trying to read through, but we will record the questions. If we weren't able to answer your question, we'll reach out to you directly. But again, thank you for today. Really appreciate your time, and I hope you found this useful. So thank you.